To remove PFAS substances from water solutions, you need to know how the PFAS molecule in principle is built up, or should I say the many different type of PFAS molecules you can encounter in water solutions. So now we're going to talk about the treatment or the removal of PFAS substances from water. Then it's important to understand how the PFAS molecules can be constructed, because the way they look will very much impact on how they perform in different steps to remove them. With that, let's go on and see how we can treat PFAS substances. Here we have our example PFAS molecule, and let's take a look at the tail end of the PFAS molecule with, in this case, 6 carbon atoms and fluorine atoms. This tail end is hydrophobic. That means it's disgusted by water, or it wants to stay out of the water solution. And one effect this gives the PFAS molecule, that this tail end could have an affinity to particle surfaces that are in the solution. Then we have the head of the PFAS molecule, and in this case it's a sulfur atoms with 3 oxygen atoms, and of course this group may change depending on what PFAS you are building or what you are working with. Now the charge, be it positive or negative, it means that this part is soluble in water. It likes water. It's hydrophilic. Also, the charge means that if you have a substance that the charge can cling to, you can remove the PFAS from the solution by using the charge at the head of the PFAS molecule. Another thing that of course is important is the actual size of the PFAS. And one example was 6 carbon atoms, but there can be 7, 8, etc. So the size will of course affect how it can be removed. For instance, through a pore or a sieve. The bigger the molecule, the easier for a quote-unquote sieve to remove it. And there is also another effect that you will see with PFAS, which greatly increase the size, not of a single molecule, but of a conglomeration of PFAS molecule, which you can see here. So the blue parts are the charge part, the head, as we spoke about here, and the tail end is the yellow marked here, and as we talked about here, we have the tail end here. The tail end will turn towards itself, and here, trying to be in a hydrophobic environment, it will, together with other PFAS molecule, form so-called micelles. And of course, one atom has a specific size or a molecular weight, but micelles will be quite bigger in size, and of course we understand that will affect the removal of a PFAS molecule if it starts forming micelles. So what other parameters can affect the removal in a solution with the PFAS molecule? Well, as always, we have a key player, that's pH. That will of course affect the charge of the PFAS molecule depending on the pH in the solution. And then we have salinity, total dissolved solid, other ions in the solution, total suspended solids, that is small particles, and of course the temperature of the solution where the PFAS is. So you have the properties of the PFAS molecule that will interact with the solution therein. So when you know what's in the solution and you know the PFAS molecule, then you can start figuring out how can I remove, how can I treat this. Now, I've labeled this the competition, but what I mean is what other ions can be in a solution that might affect the removal of PFAS. First, we of course start with hydrogen ions and hydroxide ions, the definition of pH. High concentration of hydrogen ions means low pH, and vice versa, high concentration of hydroxide ions means high pH. And the pH will affect the charge group on the PFAS molecule, thus affecting its capability of being removed. Then we have positively charged ions, magnesium, calcium, ammonium. And in the case of ion exchange, these positive ions will compete with PFAS substances that has a positively charged head, of course. And on the other side, you have the negatively charged ions such as sulfate, chloride, carbonate, nitrate, that could compete with PFAS substances that has a negatively charged head. We will come to the separation or treatment techniques in the next slide. So there will not always be a problem with these ions. They can also be positive depending on treatment method. But with that, keep in mind what other ions are in the solution will affect how we can remove, what treatment method we can choose, how effective it will be. And of course, there are several more ions than these, but I would say these are the major ions you should consider when looking at the treatment. What I mean with the toolbox is the different types of removal processes you can use for PFAS. You have granulated activated carbon, GAC abbreviated, ion exchange, IE, membranes, two sorts, nanofiltration, abbreviated NF, reverse osmosis, RO, and then you have flocculation and sedimentation, and I will briefly mention other combinations of treatment possibilities. Now, before you go to the actual process, we need to address something called pre-treatment. And pre-treatment is what you need to do before you, for example, go into a column or a filter with granulated activated carbon. And the pre-treatment is, of course, dependent on what type of raw water you are going to treat for PFAS. It could be a groundwater where the pre-treatment will be maybe none. It could be a wastewater after wastewater treatment plant. Then you need to have one kind of pre-treatment. It could be an industrial water, maybe containing lots of particles and things that would make a problem in the following step. Then the pre-treatment needs to prepare for the treatment step that you want to focus on the PFAS removal. Granulated activated carbon sounds easy enough. Just pick a carbon, problem solved. Well, as probably you guessed, it's not that easy. There are many different types of activated carbon, and you need to find the right one. And with the right one, I mean an activated carbon that has as long operation time as possible before it's saturated. That is, before it cannot absorb more of the PFAS content you want to remove. And in worst case, I've known cases where you have taken an activated carbon and it's taken 1 month until it was saturated and needed to be replaced or recharged. Many times, most of the times, you find a carbon that will last you a year, maybe 5 years before you need to replace it. So the selection of activated carbon will be dependent on the water quality that will affect how your PFAS substances can be absorbed in the activated carbon. Ion exchange. Here you have a ion exchange material or substance that has the possibility to grab on to the head of the PFAS charge and make it stick in the material, thereby removing it from the water phase. Now, this will also be dependent on what you have in your water. If you have other ions, as I mentioned before, that will compete for those active sites on the ion exchange material. Something you also need to be considering is the waste stream that you will get from the ion exchange when you recharge it. That means pushing out the adsorbed PFAS with either chloride or sodium, depending on if it's a positive or negatively charged PFAS you are wanting to remove. So here you will have a waste stream that you always need to consider on how to handle. And in my experience, getting clean water is most of the time not really the problem. Is how to handle the waste stream from the different process step that you need to work with in order to get the clean water. Membrane techniques. There are two obvious techniques that you can use for removing the PFAS molecules. You have RO, reversed osmosis, and with reversed osmosis, as probably most of you know, you will, after the water has passed through the RO membrane, have a distilled water. There will be basically no ions left in the permeate from a reverse osmosis plant. With nanofiltration, you will not hold back the one-valent ions such as chloride and sodium, but looking at PFAS organic substances, probably nanofiltration is a good way to go. But again, there are always ifs and buts in regard to this. But membrane techniques is also one way of going to remove PFAS substances. But then you need not to forget that you have a continuous concentrate stream during the membrane filtration. So depending on the salinity, the chloride content in your water, you can have a waste stream ranging from 50%, that is 50% permeate or clean water, and 50% reject, up to maybe, well, 80, maybe 90% permeate and 10-15% concentrate stream. But in the concentrate stream, you will have the removed substances, thus increased high concentration of PFAS depending on the start concentration in the raw water or the processed water you want to treat. So again, the concentrate or the reject you need to figure out on how to handle. And with membrane filtration, this is a continuous flow, so basically you need to sort out a process to finally remove the PFAS from the concentrate before you have solved your PFAS problem. Flocculation and sedimentation are classical methods for removing, well, wastewater treatment, phosphorus, or in water treatment, particulate materials such as, well, particulates and humic substances. So flocculation and sedimentation can also be applied for PFAS. I have to be a little bit careful here when I talk about this, but my guess is that with a specific flocculant, you might probably need a polishing step to handle the PFAS concentration. But flocculation, sedimentation is a possibility, given that you, as with all treatment method, you need to consider the efficiency of the method. Then I have also something I labeled other combinations, and you have ozone, which is the strongest oxidation agent you can find. So ozone will work on all molecules in the solution and PFAS chopping up in order to remove it. But here you have to be careful, what byproducts does this create? UV is another possibility, but in the next slide I will give you a reference to an article that I would strongly suggest you read. It's a review article about the possible treatment method of PFAS. And that's one of the articles I've used to put this information together for you. For you interested, I would strongly recommend this review article on different treatment methods for PFAS. It's a very good review article. So with that, we'll go on to some summary thoughts from myself. Some few years ago, when I worked with PFAS, there was a limit of 90 nanograms per liter, 90 nanograms per liter. This limit within 1 or 2 years now will be 4 nanograms per liter. So there is a very, very high increase in demands for removing PFAS. If you're looking at complementing an existing treatment process or doing a new treatment plant, waterworks, process, wastewater, in my experience, doing a pilot trial is a very good way of resolving all the issues with the water line, that is how to remove the PFAS, and also how to take care of the waste that the process you select generates. The question has many times been the cost for a pilot trial, but giving PFAS, I would say or argue that doing a pilot trial will be very, very cost efficient. So with that, I hope you had some benefits from what I presented you in regards to the PFAS and how to treat it. I wish you a very good 2024. Take good care. Bye bye.